I'm Jason Miller, and I'm going to talk to you today about scaling Vite at Shopify. I work on Shopify's largest React code base. It was bundled with Webpack. It's about 5 million lines of TypeScript and 800 routes, and historically it has been too large and too slow for us to run on our very fast local machines. And it's also been too large for us to build in CI on pull requests. And in general, it's just been painful to work on. Last year, we converted this app to Vite, and it is effectively now a Remix single-page app, still the same size, but now it's actually faster to work locally on it than it is to use our cloud-based IDEs we were relying on before. And it's fast enough to run a production build that we actually not only do the build in CI, but we run it, we smoke test it, we had extra time. And in general, it's just nice to work on. So what did we do? Obviously, we migrated from Webpack to Vite. This was a combination of hard work and code mods and also a lot of custom Vite plugins. And in general, there was a process of getting rid of custom transforms. We had a hard and fast rule. We were not going to have custom AST transformations in this bundler configuration because that way we could avoid the whole Babel parse cost in Vite. We found that Vite plugins were sort of a superpower for this migration. Some examples, we wrote a plugin to enable CSS modules for all CSS imports by default, still leveraging Vite's CSS modules implementation, but just by default. We wrote a plugin to do our bespoke translation loading. We wrote one for our GraphQL TypeScript type generation stuff, and then also one to preload the module graph, which is now actually a feature that Vite provides out of the box. There were some really interesting knock-on benefits of these. The CSS modules by default one, we actually just went to production with. We only got rid of it recently. Translation loading enabled us to kind of trivially turn around and do hot module replacement for translations, which was novel and fun. The GraphQL plugin that we wrote actually ended up giving us a foothold and making everybody aware that it was a thing. To optimize what ended up being hundreds of kilobytes of JavaScript output from TypeScript transpiled enums that were in our production bundles. And that cut the size of those bundles by 80%, which was fun. And then the module graph preloading, ours is quite aggressive. By the time you open Chrome, we've already loaded all the modules in Vite and you're just hitting a cache. So when we first cut over from Webpack to Vite, we were in for a little surprise. When we loaded the homepage, we were sending 18,000 modules to the browser. It took 30 seconds, that's being generous. It might have been more like 60 seconds to load. It was not actually that much slower than our initial load in Webpack because of some other reasons. And we did have 1 second hot reloads, which is great. But also there was definitely a head-scratching moment. Some of the plugins we wrote cut this down. So we were already at about 15,000 once we did some basic optimizations. But we were left wondering, like, what was going on? And the answer to that question is barrel files. If you're not familiar with barrel files are basically JavaScript modules that re-export other JavaScript modules. We were using them to sort of make directories feel like packages and give a bit of structure to the code base. This was pervasive. We used them everywhere. We had rules for it and the whole shebang. But we found a lot of harm caused by barrel files. The first harm that we found is a form of dead code. So if you're not familiar with dead code elimination, basically, if you assume we have some sort of an export down at the bottom where there's a constant scenario, we can dead code eliminate the thing that is now constant. We're in production, so we can delete the development thing. And you could just follow that up through the graph. So we can delete dev because it's unreferenced, dev query is unreferenced, DQL is unreferenced, and you end up with just no op. If you wrap that component in react.memo, so just basically take the function declaration, make it a function expression, and everything else held constant, now you can't dead code eliminate it because the bundler doesn't know what memo does. And so what we found is in Vite, we would end up with dead modules. This was happening in Webpack. We just didn't know. But when we switched over to Vite, this became more apparent to us. And so how this happens is, say we have a module, like the one on the left, that's re-exporting some stuff and has its own export. And then we have just a module that's using it on the right. It's only importing the use foo, so right away we can go and we can delete the unused exports. That's great. We cannot delete the imports that it has because we don't know what those are. They could be setup functions. They could assign something to window. Can't just remove whole modules. So we can delete the export of foo context because it's not referenced by foo/index.ts anymore. That's all fine and great. But its value cannot be elided because its value is a call to create context. We don't know what that is. And it passes it heavy.defaults. We don't know what heavy is. We don't know what defaults is. And we don't know what either of those two imports are. They're all going to stay in the bundle. Dead code elimination will not fix that. The second problem we run into is reduced clarity from barrel files. This really has nothing to do with Vite. It's just painful. So say we have a case where we're importing A from something called lib, and lib is a barrel file. It's doing wildcard re-exports of these three modules. We have to go through, and if we're TypeScript or Vite or a person, have to go through and figure out using a mouse and keyboard or a compiler where A comes from, which might involve traversing its entire module graph. And that's because if you're thinking, oh, it's fine, if the first thing exports A, then that's good, that's what A is. That's not true. It's actually the last re-export to export A that produces the value of A that we get on the left. So if all three of these imported, re-exported modules export A, we have to load and run them all and all of their dependencies. Another one that we ran into is accidental import cycles. This actually really bit us. So in the case here, we're importing useFoo from this module called useFoo, but the problem is useFoo, which is re-exported from this barrel file, is referencing the barrel file. It's trying to import context from the barrel file. But if we're getting to useFoo from the barrel file, it can't refer back to us. We haven't executed line 2 of the barrel file yet. We can't go there. And so it's going to try and reference the return value from this create context call that we cannot have run yet. And actually what happens is at runtime, that value is undefined. Another thing we found is this puts some strain on infrastructure in Vite. Sorry, I get some stuff in my way here. Basically, this increases the number of files and modules you're going to have to read off of disk. So that's memory usage. It's serving time. You're sending these to the browser. It increases the overhead of the file watcher because you're looking for changes in all these files. Another one is test code shipped to production. We actually found this when we switched over to Vite. So thanks Vite, that's cool. Somebody would write a test helper imports faker. They would re-export the test helper from the barrel file because, for example, our linter told them to. Now faker's in production because dead code elimination is sort of a lie. Another one that we ran into is what I'm calling bin files. I made that up just now. Basically, this is something that is sort of a barrel file. Maybe it started out life as a barrel file, but now it's not really a barrel file. It's just JavaScript. So even if we had some magic tool that could dissolve barrel files, this isn't one anymore. For us, this happened a lot because people would take imports that were static and make them lazy using React.lazy and a dynamic import, which is great. And we should be encouraging people to do that in cases where it's warranted. But it has the unfortunate side effect of making this thing now, this is just a real JavaScript module. This is not an alias of any kind. I've been asked many times if linting can help here, and the sad answer is not really. Linters get exceptionally slow when you try and abuse them for whole program analysis, like import analysis. When we were starting this project, before we had cut over to OXLint, which reduced our linting times by 100x, we were still on ESLint, and we did an analysis of our custom lint rules, and the import rule, of which there was one, was responsible for 50% of our CI time spent linting. So what can we do if linters aren't going to help? One thing you could try is installing the Debarrel plugin we wrote. This is a Vite plugin that implements a on-the-fly form of tree shaking that we're calling Debarrelling. And basically what this does is, as your modules are being served to the browser, it processes every import statement, pre-processes it, and turns it into the final locations of all of the identifiers that you've imported from a given specifier. So if you imported 3 things from a barrel file, you're going to get 3 imports instead of 1 import. And the import URLs will be the final URLs. So the barrel files are gone. They are no longer referenced when your modules are then handed over to Vite. In our code base, this reduced the number of modules that we were serving and also the size and time that it took to serve our initial page load by more than 50%. I think it's 58%. It is the single largest optimization that has gone into this code base in the last year. You can also enable tree shaking. This version of it will probably break your app because it violates a lot of JavaScript semantics. This version of it is way too specialized for you, but maybe pick and choose some stuff. We do something like this where we basically say like, hey, those imports for GraphQL files, those are going to be JSON when they're served. So yes, feel free to consider those as non-side affecting and tree shape them. We use this in combination with the Debarrel plugin. And the last thing you do is just delete the Debarrel files. I think I've made a good case for them not being worth their trouble. And the benefit that you will get out of this that the plugins can't provide to you is that you will probably find dead code when you do this, because when you delete the Debarrel file, you will find that there was modules that were referenced via re-exports in the Debarrel file, and the only way they were referenced is by those re-exports in the Debarrel file. We certainly found this. Okay, so with that all in place, we're getting better. We are down from 15,000 modules to 6,000 modules. Some time has passed, and our initial cold page load in development is about 15 seconds. Like a lot of React apps, we were basically doing a thing where we loaded most of the app up front, load the entire JavaScript and then say like, hey, React, render the app, which immediately deops out to rendering a skeleton screen and triggers critical data fetching. At this point, we've already downloaded a meg or two of JavaScript, all of our UI frameworks and tooling in order to render a skeleton screen that we sent to the HTML anyway. We just re-rendered it for no reason to get to critical data fetching. We're basically doing all the most important stuff last, which is backwards. The problem we had was all the most critical things that we were doing were entirely dependent on our UI toolkit and the UI framework we're using to render it. And so the only way for us to move forward with this was to disentangle those two things. So we created a space in our app called app context that is the new root of the module tree. React is not at the root of our module tree in this app anymore. This is actually quite similar to how React Router 6 works. We may have stolen the idea from them, just saying. So app context is basically just an object that exists outside the React tree that we instantiate. It's a place where we hoist our global concerns to, and then we just pass it into the React tree once that stuff loads. That also means that it's initialized before React and our UI toolkit stuff and all of our routing, and it runs independently of it. So while we're going to the network downloading those heavy things, we're doing this critical thing. It has the same API everywhere because it's just vanilla JavaScript. We use preact signals for reactivity there so that we can have reactivity without having it being bound to a given UI framework. And basically the way that we built this is it's just factory functions that construct properties on an object. Now our data loading actually happens pretty much right away, right? We ship like the minimal amount of JavaScript and then we're off to the network doing data loading. It's kind of like a little bootloader type thing. And it happens in parallel with our heavier UI related code being downloaded and executed. So we're doing the most important steps first and also in parallel with the less important steps. So our module graph at the root sort of looks like this. We've got the entry chunk, and then it has dynamic imports for our rendering chunk, which is the React related stuff, and our router chunk, which is the route definitions, and then that has dynamic imports for every route and every route loader. We hit a snag with this, though, a Vite/rollup snag. Because we had one entry module with a bunch of dynamic imports for the rest of the graph, the bundler very much wanted to push common dependencies up into that module. And it basically, if we had a logger that everything was using, the logger was going to end up in entry because it knows that entry was guaranteed to already have been loaded by the time you hit router or hit render. And so it's just going to move common stuff into that chunk, which seems like a good thing, right? You bloat that chunk a little bit, but hey, why would you send two modules? The problem is this creates import cycles. And so we use hashed URLs for long-term caching. And so say I go and I modify the loader for a given route. I change the API URL or parameter that's accepting. That bundle now gets a new hashed URL because its contents changed. And the router has a dynamic import of that bundle in it. So now the router's contents have changed because it has the new URL in it. The entry chunk has the dynamic import for the router. So now the entry chunk gets a new URL because its contents have changed. But unfortunately, all the routes have static imports for the entry chunk. And so they all get new URLs because their contents have changed because they have the URL of the entry chunk in them. So does the render chunk. And really what happened is like our entire graph would get invalidated pretty much every time we changed anything. Had nothing to do with route loaders. Everything imported the entry. We had this giant cycle. The whole graph was a cycle. how do we fix this? This took us a long time to sort of come up with the right methodology, but where we landed is the entry chunk can never be imported by any other chunk, full stop. If that happens, explode. And so we use manual chunks to basically each module that comes through manual chunks. If it would be in the entry chunk in that it is very broadly shared, we put it into a second chunk called common. And so the effect that this has is if I change the route loader, again, it gets a new hash, the router gets a new hash because it has a dynamic import for the route loader, and the entry gets a new hash because it has a dynamic import for the router, and then it stops because nothing ever imports the entry. We've terminated the cascade. We had to go to some efforts to enforce this. Obviously, we did the manual chunks work, but then we needed to make sure that none of the changes that were going into our code base would break this. Because again, manual chunks is a very sharp sword. And so we started to iterate on a Vite plugin that enforced bundle constraints. Basically, just before Vite was about to flush the bundles to disk, we go through all the bundles and we look at the modules that are contained in them and the code that they contain, and we find cases where nonsensical things have happened and we explode. If we ever find UI-related or rendering-related dependencies in the critical chunks, like in the entry bundle or the common bundle or the router bundle, which are definitively things that should not be waiting on those things to download, we explode the build. Another one is we identified the scenarios that can cause the cascading hash invalidation via cycles thing that I just showed, and we'll explode the build if we detect those. We're down from 6,000 modules to 2,300 modules just by reorganizing the root of the app. This is actually pretty good. So we're serving these over HTTP3. We're actually serving them locally now. And so this loads in about 4 seconds, which is really not that much slower than production, right? The rest of our journey for this it's still very much predicated on stuff we're building on top of Vite. But it is actually a lot more just about having an engineering culture of code quality and minimalism. Speaking of which, there have been some interesting culture impacts of this at Shopify. One that I'll highlight here is in the environment that we had before, where there was like a slow startup and an upfront build, and you had to stand up the backend to reference it via this Webpack dev server. We had this culture of spinning up a bunch of throwaway hosted VMs to run VS Code remote sessions against, just to do multitasking. And now we have like a 15-second dev server startup and no upfront build. And we actually built tech that uses Puppeteer to launch a Chrome instantiation that it opens our production app. But when that app sends the JavaScript and CSS, we swap it out for the Vite dev server JavaScript and CSS. And so you can actually just work on production, but with your local files, but with production data and hot module replacement. It's actually extremely weird the first time you do it, but it's like 10 times faster than what we were doing before. Okay, so I'll leave you with a demo. On the top is our Webpack setup from a year ago, and on the bottom is our Vite setup from today. So you see I've just hit save on the top. On the bottom, I've hit save like 5 times already. On the bottom in our Vite setup, HMR takes 5 milliseconds. It's all local. On the top, you see I hit save. It's about 12 seconds for hot module replacement. And this is literally editing the same file just 1 year later. So again, this is not just Webpack versus Vite. Vite was super instrumental in us enabling these things. And with that, I leave you.